Hope the coffee is good. I hope the coffee is working. Okay, I'm Michele Mauro. I work in Athens, near Venice. We are a certified good place to work. And of course, we're hiring. I also occasionally teach at the University of Padova. And as you can see, it's quite easy to find me on the web. And just a few words in advance. Opinions are mine. Most of the facts that I'm talking about are documented or documentable. You can find books, you can find sources. I'll probably mistreat a few German words here and there. Please accept my apologies in advance if you know German. And what I'm going to talk today is something that I talk about with my colleagues, with my students. They find interesting, and I think that you too can find it thought-provoking. So, it all started with a question, a very specific question that someone wanted, was answered, someone wanted very hard. We are in 1928 in Göttingen, in Germany. And for all the 10s and the 20s of the 20th century, Göttingen was the capital of mathematics in the world. And David Hilbert was its undisputed headmaster. And Hilbert had a plan. He wanted to solve mathematics. He wanted to find everything that there was to be found and to prove it. So, in its foundational book, Grundzüge der theoretischen Logik, he poses the question, can we have a mechanical method, a definite method, to decide if any proposition, for example, a theorem, to decide if it's valid or not, if it's true or not? Having such a method would mean being able to decide in a finite and certain time span if any mathematical problem or sentence was true or false. This question was so important for Hilbert that he had a name, the decision problem, or Entscheidungsproblem. For several years, the Entscheidungsproblem and all the work of Hilbert were among the most studied upon in the whole mathematical community, and sometimes even in others. And so, it's not a surprise that in 1935, the Entscheidungsproblem is one of the topics that Professor Neumann's course on Foundation of Mathematics covers in Cambridge University. His course covered anything from foundational works from Russell and Hilbert down to the latest and greatest like Gödel incompleteness theorems. And one of his students, no, that's the wrong one. Yeah, this is the right one. One of his students was young Alan Turing, that was there on a fellowship grant, and he was looking for a problem to solve for his first scientific paper. And he found the Entscheidungsproblem very interesting. And so Turing worked hard, and by April of the next year, a first draft of Uncomputable Numbers with an application to the Entscheidungsproblem was on Professor Neumann's desk. Using a truly novel approach, Turing imagined a machine that was able to make a few elementary operations, then demonstrated how this machine was able to encode Hilbert's mathematical statements, and borrowing some tricks from Gödel, he found the answer to Hilbert's question. And the answer was no. But there was a big problem. Professor Neumann had just received a preprint of a new American publication that contained a small paper from Princeton professor Alonzo Church. It was just a page and a half, but in that, Professor Church demonstrated how, from his previous work on lambda calculus, it was easy to find the answer to the Entscheidungsproblem. And it reached the same conclusion Turing reached. The Entscheidungsproblem was not solvable. However, Church's paper would have made Turing's work redundant and unworthy of publication because the subject matter was already settled. But what would a good professor do? Professor Neumann found Turing's work too variable and interesting in its own merit, and too worthy to letting go unpublished. So he wrote to Professor Church and to the London Mathematical Society to explain how Turing's solution was so different and interesting in its own, and it deserved to go on print. And so by November of the same year, we have on computable numbers with an application to the Entscheidungsproblem, part 1 on print, on the proceedings of the London Mathematical Society. This paper is what is considered, with good merit, the start of the field of computability studies, and for some, is even the start of computer science in general. On the next month, we have on computable numbers with an application to the Entscheidungsproblem, part 2, in print on the same paper. And by this time, Turing had already joined Professor Church in Princeton, where he stayed for an interesting and fruitful academic year. By the next year, in December 1937, well, some errata was needed. Turing had to race to complete the paper, so a few things slipped. And there was some pages of correction to be published. John von Neumann, that was at Princeton too, asked Turing to stay in the US, but Turing declined and got back to the UK. By this time, the idea of having a machine able to make calculations was becoming common knowledge. And Turing's machines, however, by the way, it was Professor Church that used for the first time that name. Turing machines were just an ideal construct. There weren't a practical implementation suggestion. But others were working on that. For example, we had George Stiglitz at Bell Telecom Labs that was starting to combining telephone switches to build another circuit in binary math. Or Howard Heiken that was gathering the ideas that led to the Howard Mark I, one of the first electronic computers with stored program. However, we need to take a brief step back. We need to get back a year, and we need to get back this side of the Atlantic. And in 1936, you may remember from school, the world was quite divided. And probably few outside Germany were able to pay attention to the activity of the Berlin Patent Office. That's because just a couple of days before part 2 of Turing's paper was to be published, the Berlin Patent Office granted a patent for a Rechenmaschine. That's German for calculating machine. And it wasn't a patent for an abstract idea. It was a patent of a thing that was already built and working, mostly. The author of the patent and the builder of the Rechenmaschine was engineer Konrad Ernst Otto Zuse. He worked at Henschel Flugzeugwerke as an aeronautical engineer, and his task was designing and verifying the performance of airplane wings. He had a question of his own, and his question was, why should I make all this boarding wing profile calculation by hand? Working with wing profiles requires a lot of calculation. Doing that by hand is very, very boring. And Zuse, being an engineer, set himself on building a machine to relieve himself of this task. It was totally obvious of Turing's and Church's works, but he built this machine, built his Röntgen machine, and named it Zeta 1. And then he filed a patent. The Zeta 1 had some impressive specification. It already worked on store program, almost 10 years before the Mark I. Worked on 22-bit floating point math to do the calculation that Zuse needed, and was completely electromechanical, working on relays and clockwork-like mechanism. It already had a clear distinction between memory and processing unit, something that von Neumann himself put on paper only on 1945, and all this in 1936. This truly was something very like the world's first working computer, but nobody at the time realized that. However, Zuse's work was interesting enough to obtain some state grants and work on more powerful models. And this enabled him to build more advanced design. In the Zeta 2 through the Zeta 4 models, all mechanical parts were replaced with telephone relays to have better performance and better reliability. The Zeta 3 model was later approved Turing complete in the model sense. So it was in every possible meaning a modern computer. And it could be programmed in a programming language named Plancalcul that already had features that we now associate with functional programming languages. There were even two specialized models with analog to digital interfaces that were used to control industrial processes. That's another first. Then, what happened? Turing got back to UK, and you can read books and watch films about what he did. Zuse worked at this side of the channel, and disaster happened. We know what happened. And 10 years later, we are in a completely different world. So, while Zuse survived, most of the machines didn't. And in the occupied Germany, Zuse was investigated, but was found not compromised with the regime. And so he was free to continue working. He got seed money from the IBM because the IBM was interested in his patents. And well, he founded a startup and started building computers. In fact, many German-speaking universities used his computers all through the 60s. Did Turing and Zuse met? Maybe. We know that Turing was in the mission to evaluate the positions of German scientists. We know that Zuse was interviewed among the other scientists in those missions, but we only have one oral testimonies and no written ones. So we really don't know. And well, Zuse's work did not escape German-speaking countries and had little impact on the overall evolution of computer science. With a few notable exceptions. For example, Edgar Dijkstra is known to have cited Zuse's work and once said that he brought some ideas from Plancalcul into the first drafts of the Algol language. And the very first Algol compiler itself was written for the Zeta 22 computer that Zuse sold to the ETH in Zurich. But computer science, as we probably know, went on elsewhere and went on without knowing that there was also this contribution. So what can we learn from history? From this that is our history, the history of the field we work in. Before reinventing your own wheel, you better research. Don't fall for the not invented here syndrome. Research your problem, find its true name, and use it to search, to look for it online and in literature. There is a high probability that you are not the first trying to solve it. And you'll be surprised how many problems were already solved before the 80s. If you want true innovation, you have to mingle with different people, listen to different ideas, and try different approaches. Diversity in all its meaning is key to innovation, discovery, and sustainability. Find out what drives you. What is your question? That's the engine that will keep your efforts running, and that's the compass that will give you direction. And then give a hard look to the road ahead and be prepared and willing to walk it. And please, evaluate the consequences of what you are asking for or what you are building. Think about the lives of those you would affect, and be sure to affect them for their good. If you find out that your work will harm someone, please stop doing it. Find a more useful project. Thank you. If you want to learn something more, this is a great book, very easy to read. And here are some, the Konrad Zuse archive by Zuse's own son, and a controversial but interesting article. Thank you very much.